So welcome to the first in the seminar series from the Institute of Data Science and AI. We've been running things virtually, so we're obviously a bit rusty in organizing something hybrid. So our room is rather tiny, but we'll get a bigger one next time. So these two sessions, I introduce two new academic members of staff from the computer science department. And the first speaker is Mauricio Álvarez, and I'm going to leave it to Mauricio to introduce his title. So,
okay,
Mauricio.
Okay, thank you, Magnus. So, do I still have 30 minutes, or?
This room up you for longer than you are.
I'm going to check whether there's anything else after this week, so I know we can run over.
I'm so sorry.
All right.
Okay, so thanks everybody for coming. I'm going to talk about multitask Gaussian processes. Oh, sorry, I have to say, based on the Department of Computer Science and the newly written Center for AI Fundamentals. So as I was saying before, I want to talk about multitask Gaussian processes, and then how we actually use multitask Gaussian processes for heterogeneous datasets and aggregated datasets. I'm going to come to that in a few minutes. Okay. Okay, this is working. Okay, so these are the type of problems I'm interested in. So here on the left, you have a network of sensors, and this is a sketch of the subcoast of Finland. We have some environmental stations here with many environmental sensors, for example, temperature, atmospheric pressure, the ones here, tide height. And something that happens very commonly in this network of sensors is that some sensors stop working either because the sensor fails or the network fails. So what we want to do is to use the information that we can gather jointly from these sensors to try to create a model that is able to impute data in these missing parts here. So the motivation for this, or the underlying assumption, is that because there is a common underlying sort of environmental effect going on here, these sensors are capturing sort of similar, we're looking at different parts of the same phenomenon, and then we are able to create this joint model to impute that data. I have this other example here that's very common in geostatistics. This is a very common in geostatistic problems. So this is a spatial data set, and each point here on this map is this is the Swiss sketch of the Swiss Jura region, and then on each of these points we have measurements of concentrations of pollutant metals. There was a lot of mining activity going on here years ago. And this is a setting of something called multi-fidelity datasets, where usually you will have a task with data that is very expensive to acquire, either because it takes a lot of time or because you have to invest a lot of money or expert knowledge. And then you have another task that actually is very cheap to acquire, but perhaps not at the same quality. So here with copper and lead are usually very expensive to measure, these pollutant metals, but pH level actually is very cheap. So what we want to do is to build a joint model such that at some input locations for which we only have, say, pH level at one of the pollutant metals, we're able to predict the other one. So, for example, in A, we only will have access to pH level and copper, and then we would like to predict lead, having learned a joint model, how they behave. Another example, a multi-fidelity setting is this one. So on the top panel, I have a low-cost sensor of air pollution, and I'm able to get these measurements every minute. And then on the lower panel, the black line is it's a high-quality sensor, but I'm only able to take these measurements every 10 to 10 minutes. So if I can create a joint model that is able to sort of gather the strengths of each of these data sets, will I be able to make predictions for quite high-quality data more frequent? So that's the multi-fidelity setting here. And for building these models, I'm going to use the machinery of Gaussian processes. So I feel that I have the obligation to tell you a bit about Gaussian processes. So I'm going to do that. Gaussian processes are basically generalizations of multivariate Gaussian distributions. So multivariate Gaussian distributions apply to finite vectors, whereas Gaussian processes apply to functions. So formally speaking, a Gaussian process is a stochastic process such that if I take a finite number of random variables from that process follows a multivariate Gaussian distribution. And who here is familiar with multivariate Gaussian distributions? Can you raise your hands? Okay, not too many people. So multivariate Gaussian distribution is defined by two parameters, a mean vector and a covariance matrix. So because a GP is a generalization of that multivariate Gaussian distribution, I need to define two templates to actually be able to compute a finite vector for the multivariate Gaussian distribution and a finite matrix for the multivariate Gaussian distribution. And those two templates are what we call the mean function and the covariance function. So there are some properties that this function covariance needs to follow. I'm going to skip that. So we usually use the Gaussian process as a prior distribution for functions in a Bayesian inference approach. So in Bayesian inference, you have a prior distribution that you combine with something called the likelihood function, and combining those things, you compute something which is called a posterior distribution that is actually useful to do predictions, for example. So the GP is going to be our prior distribution for functions, and we're going to see how do we combine that with data later on. So the most important, usually in machine learning, what we say is that we're going to assume that this mean function is 0, and then we care more about the covariance. And one typical example of a covariance function is the one that you see here on one dimension. So I'm assuming that x is taking one value. It's not a vector, it's just a scalar, x and x prime. And I have this shape, which is called usually as the radial basis function or square exponential or exponentially quadratic kernel. And it is defined by these two parameters as f, which is the variance parameter, and L, which is the length scale parameter. So for example, if I fix those parameters to 1, then I get this expression for the covariance function. And say that I get these values for x, the input value from x1 to xn. And what I can do with this is now I have a template to build this covariance matrix, which is given by this equation here. And what I do is that I compute that covariance matrix using these inputs. Yeah, so I basically, each of the entries in this covariance matrix is just that function evaluated for a pair of those inputs. As I said before, we assume this is a zero mean function in the prior, and then I get this sort of Gaussian, multivariate Gaussian distributions to describe these functions here. So everything that we know about these functions is in the covariance function here. And then if I sample from that Gaussian distribution, this is a multivariate Gaussian distribution, so I can take samples from that for any value of equal n that fits in a computer, then I can do that and I get this kind of shape. So you can start to see that this actually looks like functions already. Very smooth functions where this is your input and this is the function that you're getting. Each of these lines is a different sample from your function, which in this case, for this covariance is quite smooth. So I can change the parameters of this covariance function. For example, if I reduce the length scale, what I see here is that my functions start to wiggle more, to change more quickly. I can also increase that value, and I get that the functions actually change slower. I can also change the variance parameter, like this, for example, and then I can represent functions actually have higher amplitudes. That's not the only function that I can come up with. Actually, this is perhaps the one that to go to practitioners usually use this one as a first choice, but there are many other covariance functions. So for example, the Matern family, given by this expression here, perhaps you can focus on the one in the bottom, which is easier to interpret. And then it also has these two parameters, SF and L, where SF is the variance and L is again the length scale. So this is called the Matern 3-2 because this parameter B in this family here is 3/2. And then if I sample again, I get this type of function. So you can notice there is some roughness going on in those samples. So I haven't said anything about data. All what I have said is about this Gaussian object, this Gaussian distribution. But usually what we want to do is to actually do prediction. So I want to use this for data science, yeah? I want to use this for prediction, say. So the way that we do that is that we start with a kind of Gaussian prior that I talked about before, with all the assumptions that you want encoded in your covariance function. And then what you see here are just samples from that, for example, exponentially quadratic kernel again. What you see in the background, perhaps you see in the background, there is like a gray background. That's the uncertainty that I have over these functions expressed by the Gaussian distribution. And then in practice, what I will have is some data. So here I just have two data points, this point here and this point here. And what I do is that I use my Bayesian machinery, my Bayes theorem, to update the uncertainty that I had at the beginning, now combined with the data that I have to get to a new uncertainty quantification for my potential observations, which is here. So the line that you see here is the new mean process for the Gaussian process. And then the dashed lines that you see here are new samples that I get from this updated Gaussian process. And then what you see here in the background is the gray, so it's expressing the uncertainty about the given by the predictive variance. Okay, so that's a very quick intro to Gaussian processes. Now, I want to do the dependency structures I was talking about before using this framework. And as I said before, the most important thing that I need to define is my covariance function. So one simple thing that I could do is to say, well, I don't know anything about multitask learning. What is that? But I know about GPs now because I've seen 4 slides of how to do it. So what I'm going to do is that I'm going to take each of my tasks, and rather to say, oh, I'm going to learn some dependency between those tasks, is just to assume that they are independent. Yeah. So I have this data set 1 for this particular task. And for example, this is the height height of one of the sensors that I was telling you before about this network of sensors. And then I define my covariance function, and then I can compute my kernel matrix to generate these Gaussians, and then compute my posterior distribution when I have data. And I could do that for the same, for the other outputs, say other sensor network, or, you know, in the case of the Judah, then the concentration of these pollutant metals. I have a third one, I could do the same, and I could build this joint big Gaussian process, a big kernel matrix now that involves these 3 kernel matrices, 1 per output, but assuming that the terms offside the main diagonal are just basically 0, because I assume that they're independent. But that's not what we want, because we want to exploit those dependencies. So we need to find a suitable way to actually make sense of what these blocks mean. Yeah, and how do we include some sort of dependency accountability here in a way that this element is still a valid covariance matrix. Okay, so one way of doing it, this is not the only way, but one way of doing it is using this formalism of process convolutions. Yeah? So say that now a bit more formal, we have capital D of these processes or tasks that I want to jointly model. Yeah. And then I'm going to assume that each of those tasks can be expressed through this integration that you see here. So you have this integral in some domain X with this, what we call a smoothing kernel, GD, and then a latent process, UZ. And then the key here is to assume that this latent process, UZ, is one of those Gaussian process, simple ones that we saw before with a particular covariance function. And then because this is a linear operation, then your FD is also going to be a Gaussian process. And what is more important for the talk is that because you're using the same U to express all to represent all your outputs from D equals 1 to capital D, then you're introducing correlations between the representation for the outputs. And if you marginalize U in this model, then you come up, the solution to that is going to be a model that actually includes those dependencies between the different outputs. You can include more than one latent process U. So you can have more than one latent process. So for example, you could have a latent process with a long length scale if you assume that the covariance for this U is an RBF covariance. Another one could have a shorter length scale with different amplitude and so on. Okay. But if you assume that these ones are independent and still GPs because of the linearity, again, you introduce these outputs are going to be Gaussian, and then you can expect the correlation between all these outputs. So this is a very sort of cartoonish way of looking at this. So you have this latent process, then you do these convolutions with these smoothing kernels, 1 per output, and then you have the different representations for your outputs. So in this one, you have this one is epsilated more than this one. Okay. Now you end up building this type of covariances. So you are accounting for dependencies now between FD and FD prime, and that's the way that you express those covariances. Okay, good. So this is an example that we have with two of the, well, actually this problem had 4 sensors, but I'm just showing you 2 of the sensors. So on your left, this column is showing you the predictions that you would get if you were to assume that the data is independent per sensor. So I actually know all the data, and what I did was just to remove a bit of the data here. So you see this dashed line here is the real data. And I feed a GP to this, a single GP to this one, and then you see it's actually quite good following the data because it's just doing interpolation, but then for this part, obviously this is challenging task, it's not able to do a good prediction. And then another station, both of them actually should have said before, they're measuring tie height. And then I do the same thing here, I remove a bit of data here, and then obviously where you have data, the GP does a good job. It's doing just interpolation, but here you don't get very good results. Now on this column here is one of these joint models that has looked at these 4 data sets, and I'm using it to do the predictions here because they borrow information from each other. Then actually the prediction is quite good. So this is the multitask approach. Any questions so far? Okay. So we wrote this monograph some years ago where we talk about all these models for kernels for vector value functions. Now, I want to use this multitask in those particular settings that are very common in data science. So one of them is, for example, when you have several variables changing across an independent variable, so it could be space, time, but those variables have a different nature. So one of them, for example, could be count data. One of them could be just continuous data. The other one could be just binary data. But you know that somehow they are correlated and you want to exploit those correlations. This is what we call heterogeneous data sets. And the model we refer to as a heterogeneous multitask learning. So this is a very nice application. I was working with some colleagues in Spain as part of this work. Is on human behavior data. And because we have our routines in our life, if we were to just wear, have a GPS in our watches or something, we will see there are a lot of common patterns in our daily activities during the week and during the weekend. And what they wanted to do was to use that to actually monitor patients that had some sort of mental health condition to see whether they could spot some sort of particular behavior that would require to have a specialist on site where these people were living. So they had these smartphones and they had these variables that they were measuring. So they had lots of variables. We just look at these 3 variables. So one of them was a binary variable telling us whether the person was at home or not. This one was a distance from home. So it's a continuous variable. And this one was whether the person was using WhatsApp or not. There were other ones like how many apps this person had open in the smartphone and so on. So we know somehow that this might be correlated because they're coming from the same patient and expressing perhaps some underlying condition. And then what we wanted to do is to use this multitask learning together with a suitable representation of these outcomes so that we could do data science, basically. Yeah. So this is the model that we have. Again, we have 3 different tasks. But now what we're going to do is to allow each of the tasks to have a different likelihood function. Yeah. So this would allow us to represent different types of data, really. So each of these likelihood functions is going to be defined by some parameters. And what we do is that each of those parameters is sort of represented through an underlying GP. And we have to use some nonlinear transformation of those underlying GPs so that the parameter for that particular likelihood is within the range that is supposed to be. I'll give you some examples later. Okay, and all those underlying GPs, basically what we do is that we put a multitask learning prior over them, one of these multitask GP prior, so that we can account for all the dependencies between these different outputs. Okay, so here is just to put some names to this. So say you have 3 outcomes, three outputs. One of them is binary, the other is a count variable, the other one is a real variable. And then for the binary variable, you assume you're modeling with a nullity distribution for the probability that is equal to 1, and they usually use the sigmoid function, and the input to that sigmoid function is given by your GP. And then a Poisson you could use, for example, for a count data set where the intensity parameter is a transformation of the line Gaussian GP, and just make sure that that parameter is always positive. And then you have a third one, which is a heterogeneous Gaussian, where you allow both the mean and the variance to change with the input location. So in this example with 3 likelihoods, you will have 4 parameters. So 4 parameters then represented indirectly through 4 Gaussian processes, and then we put the joint multitask P over these 4 Gaussian processes. That's the way that we include sort of those dependencies in this type of models. And then, how long do I have?
5 minutes.
Okay, and then we have to do Bayesian inference. But Bayesian inference here is not as straightforward as it was in the regression case. So we have to come with these more sort of sophisticated ways of doing Bayesian inference. This one is called variational inference. Basically, what we do is that just to find an approximate sort of posterior to the real posterior by minimizing something called the evidence lower bound. I'm not going to go through the details of this, obviously. We combine all these with something called inducing variables, which allows us to do large-scale data sets. The details are in the paper. I'm just going to skip to these results then. So this is the human behavior data I was showing you before, and we did sort of a similar experiment where we just removed some data for some of the outputs and then look at the prediction that the model would do on those data, those parts of the data were removed. And we assess this in terms of performance metric called the negative log predictive density. Lower is better. So you see that in those variables that I showed you before, those 2 binary variables, one of them actually do better than this other model, which is just looking at independent for each output. And then on average, we are better. Okay, this is another example where we're looking at this spatial data set of London house prices, and the 2 variables that we were modeling were the type of contract, which is a binary variable, and the other one is the sale price. And then these are the predictions that we do with our model. So this one is the probability of the freehold, the type of contract, and then this is the log price, the variance of the log price. Also, again, compared to this chain model, we see that we do better. Right, so if you want more details, this is a paper we published some years ago. And now the last bit I want to talk about to complete the talk is about aggregated data. So as I said before, you have data that many settings in data science, you will have like one sensor measuring every minute, another sensor measuring every 10 minutes, or you have a spatial data set where you take, this happens in demographics data sets where, maybe some variables are measured by postcode, but other variables are measured by individuals, etc., or by neighborhoods. And then you want to combine all those into a model. So basically, the idea is the same. The only thing that changes is that prior to using these latent processes, we integrate them over the support, the compact support or the support that we want to refer to that data set. So to that output. So for example, you have a data set that is measured in I don't know, in every minute. Perhaps this is going to be just 1 minute of length for time. And then for the other output where it's measured every 10 minutes, this is going to be integrated over 10 minutes. And then just going back to the initial example that I had, in this panel, we are measuring the variable every minute with a local sensor. And then in the bottom, we are measuring this variable every 7 to 10 minutes. Is the black line that you see here. And then we use both data sets to actually infer what had been the actual high quality data. So the true high quality data is this red one that you see here. And the prediction number model is the blue one here, with some sort of confidence credible intervals here. Okay, I think I'm going to stop here. Thanks.
Okay, time for a quick question. Yeah.
So I'm a postdoc from NLP background, learning processing. I wonder whether you can use the Gaussian processing for NLP tasks, for example, the main function and the covariance function you mentioned. I was thinking it might be used for mixed domain and the domain specific NLP data.
Yeah, maybe. Yeah, I mean, like people on you might want to follow the work of Karl-Heinrich Eck, because he has looked a lot about these type of models where you can express something with a joint model and then having private models for each modality.
And then you mentioned criteria. Do you think medical data belongs to category or not?
Definitely, yeah. Medical data, yeah.
I like the person name on the research.
Yeah, I guess so.
Any more questions or wave hands? Yeah, go on.
So when you're, sorry, I was late because it will be fine, but I think I got the gist of it. So when you are building the multi-task regression model, do something in the convolutions, in the coefficients of the convolution tell you about the importance of each input or each output. And I mean, you're assuming that there is a relationship between the outputs.
Yeah.
And it might be cases that the relationship between some outputs is stronger than the relationship between other outputs.
Yeah.
And can you say something after you build the model to identify that maybe if you remove some of the outputs, actually you could get a better model of the others?
Yeah. I mean, like this thing that I explained here is like the very, very basic fundamentals. Yeah. But there is a lot of research on top of this looking at that kind of question. Yeah.
Allow you to explain.
Yeah. I mean, there are all sorts of problems because you could also be assuming things that do not exist, like imposing sort of dependency where there is no dependency. So those kind of objects, as you were saying, will give you some idea whether that's perhaps wrong or.
Okay, thanks. I think we better move on to wave hands to be fair. So you both just the same amount of time. So wave hands started recently as a senior lecturer in machine learning, also in the Department of Computer Science. And he's going to talk about Bayesian reinforcement learning for robot control. So over to you, Wade, if it's all working.
Where to hide this?
Is it working?
Oh, that's the question. One more question. Oh, any insight from London housing price analysis? Any buying suggestion? I think how to hide this.
Yeah, under more, I think there's not.
Yes. Yes. Yeah. Good. Okay. Good afternoon, everyone, and thanks for waiting. And today, we're gonna talk about Bayesian reinforcement learning for robot control. So I say Bayes is for Bayesian, who was born like 17th centuries, so it's like 300 years ago. And the Bellman is for reinforcement learning, who was born in 1920 in the US. And Lyapunov is for control, so who was born around 18th centuries in Russian Empire. So basically today, I'm gonna use the 300 years of knowledge from 3 different countries for robotics. Let's see what happens. So this is the outline of this talk. First, I'm gonna give some introduction about myself and about my research. Then I'm gonna meet with the first 2 persons, Bayes and Bellman, regarding Bayesian reinforcement learning. So Bayesian reinforcement learning can be used for control. And then later, we'll introduce the 3rd person, Lyapunov. Why? Because for robotic control, it often happens in the safety critical scenarios. So we need Lyapunov to give us the tool to show safety certificate. And the last, I'm going to show some demos from different applications from air, land, space, and cyber. So I'm Wei. I got my degree in control engineering from China, and I got my PhD from Imperial, working on system and application. Then I moved back to China, work for the drone company, DJI. Then I moved to Netherlands, work as assistant professor in robot dynamics in TU Delft. And recently, a couple of months ago, I moved to Manchester as a senior lecturer in machine learning. Right, I work on robotics. I think to start with, maybe I can show you something that recently Tesla is working on humanoid robot. Let's see what's happened.
Yeah, with the degrees of freedom that we expect to have.
Yeah.
Welcome.
So we can see that Elon Musk is pretty happy with the product, but I think we are not happy because it's not that impressive, because somebody can hold it and humanoid robot is not working autonomously. But I do acknowledge the inspiration that I think people around, I think many people had a dream of pursuing a unified theory of artificial intelligence to create a general intelligent agent for the well-being of humanity. And my goal is to use the robot to realize the universal agent with autonomous perception, cognition, decision-making, learning, control, and social cooperation capabilities, which are in line with the safety, security, privacy, human emotions, ethics, and moral concept. And my focus is more on the learning and control part. I play a lot with different kinds of robot. Well, my research touch upon decision-making and precision and perception. And I'm happy to find that many colleagues in Manchester are working on the other different aspects, which help me to achieve my goal. And I believe beyond the humanoid robot, this artificial general intelligence agent can be implemented across different robot platforms for particular applications. So what exactly am I doing technically? So to control a robot is very much like we control our arm, to move the fingers from the right point to the green point. Okay, so the visual information of the arm and our finger will be transmitted to the visual cortex. Then a motor signal will be transmitted to a cerebellum, okay? Combined with the proprioceptive state, for example, the position of the arm, the angle of the arm, a control command will be transmitted to our muscle to drive the muscle and drive our finger to move. How to translate into robotics? Well, if you want to control a robot, you have to understand how the robot works. That is to know the dynamics of the robot. And also, we want to track our finger. It's preferably we can predict the motion of our finger. This is known as system identification and state estimation. That is from state to dynamics. On the high level part of our brain, so that is used for planning and control. However, robots are different from human, right? So it's it's a piece of hardware. So you have to adapt the algorithm and implement the algorithm to the particular app, the particular hardware, and to adapt the deployment. And my research group is focusing on using machine learning for robot control. And we made contributions in these three important pillars. However, the conventional machine learning cannot be used directly to robot control because we don't have a lot of data. And we really need an accurate estimate. Preferably, it is a distribution, which can help us to quantify the uncertainty. And most of the time, we don't have expensive computational resource. We just use the robot, and we have the mini chip, then we have a very limited resource. Of course, you can use the cloud resource to do the computation, but you have the problem with the communication latency, or you have the vulnerability for cyber attacks. And we found, and we believe, Bayesian learning is very promising to solve these challenges. So our aim is to build robot Bayesian brain. And we believe this robot Bayesian brain can be used and implemented across different robot platforms. So recently we joined Manchester, and we found that Manchester is very strong in robotics. And I believe together with my colleagues in the Center for AI Fundamentals, that we can be the enabling factor to push forward the development of robotics in Manchester. Okay, so when I talk about machine learning for robot control, I mainly talk about reinforcement learning. So what is reinforcement learning? Why reinforcement learning, and why not reinforcement learning? So reinforcement learning sits at the intersection of many fields of science, and each of these fields has a branch that is trying to solve the same problem as RL. That is the science of decision making. And there's no supervisor, only a reward signal obtained by trial and error. The time really matters. So essentially, it is a sequential decision-making problem. And as you can see from the media, from the social, from the TV and the magazine and so on and so forth, reinforcement learning has achieved a very impressive performance in many different tasks. For example, beat championship in Go. So what is reinforcement learning? So in reinforcement learning, there is an environment, there is an agent. So let's take an example of robotics. For example, you want a drone deliver some parcel from point A to point B and maintain in this desired height, okay? So the environment is actually the robot per se. So This is the dynamics of the environment, but also the altered environment around this drone. And you have the state. States like the head, the velocity, angle, and so on and so forth. And you have the reward. Reward is like the distance between the actual head to the desired head. All right. So the environment of the robot transmits the state and the reward to agent. Agent is like an algorithm. So it's smart or the intelligent thing to tell the drone to where to fly and how to fly. So it's the algorithm inside the drone. All right. So this agent takes information and generates some control action to tell the drone, okay, go fly this way, then interact with the environment, so on and so forth through trial and error, and hopefully we can learn a nice control strategy to drive the drone from to deliver the parcel. And there are states, for example, more mathematically, there are state S, action A, policy pi. We have the data trajectory, basically sums the data from 0 to a long time in the future. Then we have the reward, and all the things, all the environment can be modeled as a markup decision process. So it basically says the next state depends on the current state and the current action, not before. And then we can write the probability of a trajectory as follows. We have the return. So we not only focus on the current reward, we want to sum them up into the very future. And the most likely, we're going to focus on the recent reward. Well, we're going to focus less on the future reward. So that's why we have the discounted return. Then we have everything. So the Z here is called state action pair is STAT, state and action. So we can write the state action transition dynamics. Well, there are two important functions. One is the action value function, which is the expectation of the discounted return given a particular action. And the state value function is expectation of the action value function given a particular policy. If you sample all action from this distribution of the policy, you can get expectation of the state value function. Then advantage function is difference between the action value function and state value function. And our objective is the expected return under the policy pi, which is the expectation of the discounted reward into the future. So our goal is actually to sample these data set, these trajectories, and hopefully that we find a policy pi which can maximize this objective function, and we can train a next policy or controller to try to control the drone to move smoothly as quickly as possible to the desired height. However, to maximize the return, the expected return is difficult because you're going to sample a lot of data. So you're going to have the problem of curse of dimensionality. So that's why we're using the value as approximation for the expected return to maximize that to get an optimal policy. All right. So that's why we're going to use the celebrated Bellman equation, which you solve recursively from backwards, as in we do in dynamic programming to get an optimal value function. Then after that, we get Bellman optimality equation to get an optimal policy. Okay. And there are many methods to solve that. I will not cover that. For example, like a value function method, policy search method, and you can combine the value function method and policy search method as the active critical method. And there are also model-based RL and model-free RL. So essentially, they are all machine learning methods. But the difference is that in model-based method, you try to learn the mathematical model of the environment and use the model for planning purpose, which is more data efficient. Okay. Okay. RL is good. RL is impressive, but there's a problem. The problem of reinforcement learning is that there's a lack of certificate for performance guarantee. So the control performance will deteriorate in adversarial scenarios. For example, uncertainty propagations from sensors to actuators, cyber attacks, external distances, or arbitrary safety and physical constraints, right? And more formally, certificate can be defined as the formal and explicit proof to guarantee control performance under the generated actions in adversarial scenarios. For example, there are detection duration, recovery duration, resiliency, robustness, and steady state error, and so on and so forth. And in this talk, I will focus on the safety constraint. Okay. So why Bayesian learning? Can Bayesian learning be the remedy to solve these challenges in reinforced learning? Well, the answer is yes and no. But before we introduce Lyapunov, we definitely need Bayesian learning. So thanks, Mauricio, that introduced the Gaussian process in the Bayesian learning from scratch. So I'm going to skip that. But in Bayesian learning, basically, you have a prior, you have a likelihood, you have posterior, you want to maximize the marginal likelihood, evidence, and so on and so forth. So, okay. Of course, there are some advantages because if you're using the Bayesian learning, you can capture the uncertainty by probability distribution, right? So you see the error bar in Mauricio's slide, right? And also, it is a natural optimization for exploration and exploitation trade-off. And it's a unified framework for many other learning methods like plain reinforced learning, inverse reinforced learning, multi-agent reinforced learning, imitation learning, active learning, and so on and so forth. However, Bayesian methods are sporadically used in RL. Why? Because the most important thing, or I think the first thing to do is to specify a prior, but there's no guideline to specify prior for reinforcement learning. So how to specify prior? On model parameters, on value functions, on policy, and so on? Well, challenge means opportunity. So the question we want to ask is, could desired control performance related properties as shown in the previous slide be encoded as priors? So at least if we're not solving Bayesian problem, at least we have some kind of working optimization problem. So think about the lasso, the L1 regularized linear regression versus the Bayesian linear regression with lapsus prior. Good, let's try that. So as you can see, I mentioned the safety, right? So what exactly is safety? So we're gonna meet the third person, Liap from control, that show how to construct this prior and how to show the theoretical result, how to construct the certificate. So let's move to the control. So everything is deterministic now. So typically a robot can be described by a differential equation or a difference equation, right? So think about everything is deterministic. We don't have probability because probability is 1. So everything is deterministic. And stability certificate is like you can construct a control Lyapunov function V, which is positive. It's a scalar function, and the derivative over time or the difference over time for the discrete time case is non-positive. Well, for safety certificate is that you can construct a control barrier function which is non-positive in the safety side. Okay, it is positive in the unsafe side, and the derivative over time or the difference over time is non-positive. So this is decreasing over time. Okay, this is decreasing over time. You can also unify the stability and the safety certificate by constructing control Lyapunov barrier function, which is as follows. So it's very similar to the previous two. So the derivative of this control Lyapunov barrier function over time is non-positive, and the difference over time is non-positive. So how to obtain the certificate? As I said in the previous slide, you have to construct. So construct means that you have to use your intelligence to labor design a function. So that's why we call it construction. There's no automatic way. So it is a long story and long-lasting research in control theory. But for us, our idea is that we want to learn the certificate from the data in Bayesian reinforcement learning. So first, we want to force the value function to be the certificate candidate. And the second, we want to specify a stable and a safe priors on the value function. Here it is the key. Value function is the certificate candidate. So we'll focus on the control Lyapunov barrier function. Then we specify a control Lyapunov barrier function as the value function. Then we can construct the prior distribution PV encoding the following inequalities in control Lyapunov barrier function. Okay. Then if we can construct that, we can use the Bayesian, simply use the Bayesian rule to guess the posterior of the value function over the observation, basically the reward. So how to learn a safe value function? Okay, and in the following, it's a bit technical, so I try not to convince you to understand everything, but I try to follow that for the purpose of recording and to get to know that what is really going on. So basically, you can use a tempo difference learning. Then you can stack the observations from t from 0 to from t. So essentially, you try to solve a linear regression problem. But how the key step is encode the energy decreasing inequality as constraints. So we can encode this first order difference function B to represent the difference of the value function over time. And we can encode these energy decreasing inequalities as a constraint as a constraint for the regression problem. However, there are two problems. The first problem is that V and Q are in function space. And the second, V is the constraint and not Q. I think due to, I think the key idea is that we want to make a plan to get a V and a Q. So first we specify the V and the Q as Gaussian process. And the second, we want to get a posterior estimation of the certificate. First, in the constraint case, we can derive Q from V. With this understanding, we can move on. In the constraint case, derive Q from V and this BV, that is this distribution, right? Then we can use the policy search. You can use the policy search method for obtaining the Q. Then we are done. So I think due to time limitation, maybe I just skipped the technical part. It's a bit complicated, yeah. But okay.
Slow down on Zoom if you want.
Anyway, this is not a show off, but I want to show you that, okay, everything is rigorously derived. So everything is actually analytical. So you can use result with very high confidence. So just, I think it's too blank to say the theory. Let's see the demos. Okay. So we try different things. The first, we try the order to 2D navigation. So the idea is that we want the journal fly from around this region to this region without colliding with the obstacles. This is difficult because the geometry of the obstacle is strange. So it's very challenging for the conventional path planning or motion planning algorithm. So let's see what happens. You see here, this is actually not wrong because there is a function to push the drone beyond the obstacle. Yeah, there we go. And the next, we also try on the autonomous driving land application, which is safe reinforced learning for UGV control. So we want to design an end-to-end algorithm to drive a car in different scenarios. So let's see the demo. So we try on the off-road uneven surface, and also you can see that there is an obstacle here. So try to avoid the obstacle and go smoothly in the urban area. And also we extend to the multi-agent case, which is the leader-follower. So this is the leader, this is the follower, and the follower want to follow the leader in a strict line without colliding with the obstacle. And here they want to track a circle with collision avoidance. Yeah. And the next thing is space. So this space is a bit interesting because this one is pushed air. It's called air bearing test bed. So think about this is the satellite, and this is space station, and this is like an astronaut. So when the docking to the target, you try to avoid this astronaut. And let's see what happens. So there are three stages: operating, proximity operation, and docking. So this is the Bayesian reinforced learning with control layout and variable function priors. Good. And this is a comparison with the classical method in motion planning and the path planning. Yeah. And this is a well-known model predictive control for control of, for example, autonomous driving. Because MPC requires a large amount of computation, so this kind of thing just doesn't work. And the last, I want to show a secure control under cyber attack. As I mentioned, if you're using a cloud, you want to use the GPS, then there's a vulnerability for the cyber attack to the sensor from steal the sensor data or change the actuator data and so on and so forth. And in this setup, for example, there's a hacker and try to eavesdrop the sensor data and change something to the computer to change the command of this vehicle. And let's see what happens. This error control is like, this just a wiggle around. Okay, it's weird, but for this one, it looks pretty good. But although it's not perfect, but it still kind of slowly wiggle around. But yeah, it works. So conclude. So there's a beautiful marriage between control theory and machine learning, and we can use, especially using the Bayesian learning, we can apply successfully for robotic control. And for future directions, and one thing is a theory, because there are so many performance things we're gonna derive. And on the machine learning side, we have to show this convergence and sample complexity and so on and so forth. And the second is actually everything we show here is fully autonomous, but very important thing is human in the loop. So how to collaborate, how to make the human collaborate with the robot is one important direction. And the last is application at scale. So beyond this, we just show some demos on some robot. But I think for application at scale, for example, to solve some of the most challenging problems in energy, climate change and so on and so forth, need collaborations. And I believe that we guys can collaborate together to make Manchester the best place for robotics, machine learning, data science, and AI. Thanks. One more thing, the simple message. We want to make robots intelligent, also under control. Thanks.